Hello, here are the quiz answers to chapter 28, Sources of Magnetic Field. And number one, you have to find the magnitude of the magnetic field due to a straight conductor. Direct formula, just substitute the numbers. Remember that mu naught is 4 pi times 10 to the minus 7. And of course, distance is in centimeters, you'll have to change it into meters. And you get the answers 1.5 times 10 to the minus 5 Tesla. And the second one, the currents are flowing in opposite directions, and the magnetic field here, due to both the currents, is going to be in the same direction. According to this diagram, it's going to be both out of the screen. So you got to add up both the magnetic fields. So find the individual magnetic fields due to the straight conductor and add them up. Now that is due to the first one. The reason why I've written 2 here is because mu naught is 4 pi times 10 to the minus 7. Okay, so I have to add 10 to the power negative 7, which I have forgotten. Now I'm doing it. Okay, I have to add 10 to the negative 7. And you get the answer as 5 times 10 to the negative 5 Tesla. In this third question, you have 4 long parallel wires, each carrying 2 amperes in the same direction. And I'm assuming that all those currents are out of the screen. And, the distance is 4 centimeters. And let's try to find the magnetic field at this point. Now remember that due to this conductor, the magnetic field here is going to be at right angles to this line joining them, which will be right this way. But due to this conductor, will be at right angles to this line, which has to be this way. And due to this one, it has to be along this way. Okay, so I'll label them A, B, C, D, and let's first find the magnetic field due to A at this point. It's a straight conductor, so that's the formula. And when you plug in the numbers, you get, alright, the current is 2, the distance is 0.04 in meters, and you get 10 to the negative 5 Tesla along that direction. So that's BA. Why? Because it's perpendicular to this line joining them. Now BC is going to be exactly the same in magnitude. So BC is equal to BA, but it's perpendicular to the line joining those two. Okay. And now the magnetic field here due to, did I call it D? I was supposed to call it B. Okay, that's BB. So that will be, the distance here is 4 root 2. And that is what comes out to be 5.65 in centimeters. So 0.0565 in meters. So that I get as 0.7 times 10 to the minus 5 Tesla. Now you got to find the vector sum of these 3. And so first find the resultant of BC and BA, which is going to be exactly along this line. Now find the resultant of these two. And then add the third one to that, which is 0.7 times 10 to the minus 5. So when you do that, you get 2.1 times 10 to the minus 5 Tesla. Number 4, a solenoid, 400 turns, radius given, length given. Find the magnitude of the magnetic field. Straight question, direct substitutions, and you will get the answer as 0.015 Tesla, which is 15 millitesla. 6. Oh no, that's number 5. You have a wire of thickness 5 millimeter that's tightly wound 200 times. Now each one has thickness 5 millimeters, so if you multiply 5 times 200, you're going to get the length of the solenoid. That's the idea that you need to have. 5 times 200 is 1000 millimeters, which is exactly 1 meter. So once you find the length of the solenoid, then you plug it into the formula mu naught I by the length. And you get 2.5 times 10 to the minus 5 Tesla. Now in 6, you have a toroidal solenoid, and the radius is given, that's the radius that's given, 0.5 meter, and a cross-sectional diameter equal to 10 centimeters. When a current I passes through the coil of the solenoid, the magnetic field at the center. So what do you mean by center? It's not here, okay? The center of the solenoid is right here, center, exactly the center of this. And that's given, and you got to find the largest value of the magnetic field for the same value of the current. Now the largest value is going to be at the inner edge. The smallest value is going to be at the outer edge. What we are given is the magnetic field between those 2 points at the center. So keeping that in mind and applying the formula for magnetic field at the center, you can first calculate the current. Make I the subject, and when you plug in, radius is 0.5 and micro Tesla. Well, let me change the micro Tesla into Tesla, so you have no confusion. So that is 2 times 10 to the minus 6. And after all cancellations and calculations, you get 5 by n, because you don't know the number of turns. And the field, as I said before, is largest at the inner edge. Okay. And at the inner edge, the radius is going to be 0.5 meter minus 5 centimeter. Because remember that the diameter is given as 10 centimeter, right? So half of that, 5 centimeters in meters, is 0.05. So the radius is 0.45, the inner radius. Now recalculate the magnetic field using the inner radius. So keep n as it is. I is 5 by n, 2 pi times 0.45, okay? So notice that the value of the radius changed, because now we're using the radius, inner radius. And you get it slightly higher, you get 2.22 micro Tesla is the answer. And number 7, circular loop, find the magnetic field at the center. Direct substitution, mu naught Ni by 2a. N is 1, of course, because it's just a loop. A is the radius. 10 centimeters is 0.1. That's why you have 0.1 here, 10 centimeters. 3.8 times 10 to the minus 5 Tesla. Semicircular wire radius R connects 2 wire segments as shown. Okay, so those are the 2 wire segments. And that's the semicircular wire that connects them, and you have to find the field at the center. We know that the field due to a circular loop is mu naught I by 2r. Because it's a semicircle, you're going to take half of that. So that will be mu naught I by 4r. That's it. This question is a concept question. The magnetic field produced by a long straight current carrying wire is, of course, proportional to the current in the wire and inversely proportional to the distance from the wire. And this again is a concept question. The ampere is defined using the force between current carrying wires. Okay, you cannot have D as the answer. That's not correct, because the ampere is actually coulomb per second, not per second squared. So it's not D. The answer is E. And here, in using Ampere's law, the integral must be evaluated around a closed path. Yes, around a closed path. Brings us to 12. A straight wire carries a 12 amp current eastward, and a second one carries a current 14 amperes west. Wires are separated by 42 centimeters. Find the force per unit length on the wire. So unit length means the length is 1 meter. Alright, that's the diagram. And force between conductors, parallel conductors carrying current, is given by this equation. You know both the currents, 12 and 14, and the length is, oh, no. Well, I have to, yes, the length is just 1 meter because it says per unit length, and you get the answer as 8 times 10 to the negative 5 Newton per meter. 13th question is, what is the value of the magnetic field at the center of a square wire of length A on the side if the current in the wire is I? So you have a conductor bend in the form of a square like that, and you've got to find the field at the center. Just calculate the contributions to the magnetic field due to each segment. Alright, so field due to each side or each segment is going to be same in magnitude. It's given by mu naught by 4 pi I by r sine theta 1 plus plus sine theta 2. Okay, that's the equation that you have to know. And in this case, the radius is just a by 2, and the angles are all going to be 45 degrees. And therefore, due to all the 4 of them would be that quantity. Yeah, actually it is 1 by root 2 plus 1 by root 2, right? Which is root 2. So I had made a mistake on that. So due to all the 4 would be 4 times that. And you get the answer as 2 root 2 mu naught I by pi. That is the answer. 14. The figure shows the cross section of a hollow cylinder of inner radius 5 centimeter and outer radius 7 centimeter. And a uniform current density 1 ampere per centimeter squared flows through the cylinder. Calculate the magnitude of the magnetic field at a distance d is equal to 10 centimeter from the axis. So you are trying to find the magnetic field at this point. is 10 centimeters away from the axis, which is this point, okay? Now, because you're given the current density and it's defined for 1 centimeter squared, you have to find the area of the material first. And the area of this material inside is going to be pi outer radius squared minus pi inner radius squared, right? So find the area. And now you know current is J times A. Current density is 1, so multiply with the area. Remember, both are in centimeter squared, okay? And you get the current as 75.36. Once you get that, use the formula for magnetic field due to a straight conductor. And use the current that we just calculated, 2 pi times the distance, which is 10 centimeter or 0.1, and you get 1.5 times 10 to the negative 4 Tesla.